Excuse me, just one little thing. When you have questions, please let me know. I will bring the microphone because we are on streaming. And if you don't have the mic on, your questions and answer will not be listened. Thank you.
On the theoretical and practical limits of digital QSOs. First, we will speak about the required energy to transfer 1 bit from the transmitter to the receiver. Then some words on codes, especially for radio amateur weak signal modes. Then we will hear a little bit about synchronization and phase recovery. I told already on that point on the last EME conference in 2014, so I can make that very short. The fourth point is QAM11, a new mode which I designed. It is not quite ready, but working on the simulator and working very fine. I will compare that to FSK. And the last point is the limits of correlation, which is deep search. This is a new point, and nearly all slides will be different from those in the paper. So please look at the slides here. So let's start. Weak signal communications systems usually are evaluated by the relation required energy per information bit divided by noise power per hertz bandwidth. This EB by N0 is, in an optimized BPSK receiver, the SNR at the input of the decoder. On the other hand, radio amateurs use the SNR at the audio output of an SSB transceiver in a bandwidth of 2,500 Hertz. The transformation between both scales are given by these two relations here. The threshold sensitivity for full decode of the message in JT65 in a bandwidth of 2,500 Hertz is minus 24 dB about. And if we put the values, bits of the message, oh, I see, 64.8 is correct. And the bandwidth here, we get 8.2 dBs at the input of a BPSK decoder. That's a good signal. C. Claude Elwood Shannon found by mathematical treatment that confident communication only is possible if this value here is larger than logarithmus naturalis of 2, or in dB, it is minus 1.6 dB. That's the general Shannon limit. Applied to the usual EME case of transmission of about 70 bits within about 50 seconds, we get the minimum possible SNR in bandwidth 2,500 Hertz for communication at 100% correct decode. The SNR must be larger than minus 34.1 dB. This is the Shannon limit for weak signal modes with these parameters. Therefore, theoretically, a gain of 10 dB over JT65 could be possible. But the mathematical treatment of Shannon did not say that it is practically possible to approach this value. The real practical lower bound might be much larger. Now, for the next discussion, we need some usual terms. The number of information bits, say these eight information bits, The number of information bits usually is noted by K, and these bits are encoded into a block. The block is encoded information of n bits, in this case 16 bits, and the ratio R, K divided by n is a code rate. In this case 1/2. With these terms, Shannon refined his lower bound in 1959 as a function of the number K of information bits and the code rate R, and finally of the required block error rate, PW, that's an old notion, probability of word error. Today we say block error rate, BER, so that's the same as PW. This lower bound is the sphere packing bound. It is dependent on these parameters, so it is not a general bound, it depends. And I show an old figure of the JPL. Here are some space probes. You see the Galileo low-gain omnidirectional antenna. The high-gain antenna, you know, could never be unfolded, so everything from Jupiter had to be transmitted by an omnidirectional antenna. Cassini here, and the sphere packing bound for 0 code rate is this black line. All practical communication systems are well above this line. No, of course, is below. But this is for the impractical code rate R, 0, which means infinite long blocks. Therefore, I add in this diagram the sphere packing bound for practical codes are 1/2, 1/3, 1/4. And you see the space probes come well near to this theoretical bound. So there is nearly nothing to make better. Now you can ask, where are our modes? In this case, we have PW 10 to the minus 4. That is 1 decode error in 10,000 transmissions. All what we use is above the diagram. The only is PSK2K. It is designed especially to come near to the limits, and my new mode QAM 11. The codes used in these both modes are here. So the codes are excellent. They are even better than anything else in the diagram. But the modes themselves are at least 2 dB above the codes. We have to discuss that in this small lecture. The typical parameters of weak signal communications are very different in deep space probes. We have information of about 10,000 bits per block, and they send one block after the other, so they only have to synchronize once, and then the signal can well be tracked. The block error probability is 10 to the minus 4. In our EME case, we send about 70 bits, and we are happy if every second decode is successful. So the block error rate, 50%, that is my value, which is relevant for amateur radio. The JT65 deep search is completely different, a different number of information bits between 1 and 12, and the block error probability must be low because there is no error detection, and that forces us to use about this. I computed a completely new diagram for just this case. Block error rate 50% on the AWGN channel. That is a Gaussian channel without phase distortion. The Shannon limit is here, and the lower bound for 50% correct decode even is a bit lower. You see here different modes. The uncoded BPSK does well perform, and even if we use 1-bit parity, it is a little bit better. The PSK2K modes for 2, 4, and 6 meter are here, and QIM 11 is here. So we will have to discuss why are they not at that place. Some words about codes for radio amateur weak signal modes. I make it short here. I only use convolutional codes as an example. Convolutional codes are a large class with selectable code rate, 1/2, 1/3, until 1/16, and then it gets impractical. And I only show this graph. It is different from what I show in the paper. There are 3 parameters of codes which are relevant to us. The main parameter is the required energy per bit. This is to minimize. The second parameter is the decoding time. We cannot use codes where the decoding time is larger than a year. Yeah, Joe's codes with constraint length 32, if you use the Viterbi decoder, what I do here, then you come in that, on that number. But Joe uses sequential decoding, which is much faster. I put here several coders. The magenta codes are code rate 1/2, so very simple codes. The blue code are 1/16, and don't forget this black, it is only to show that there are even better codes. And these codes are shown here in 2 different modes. The solid lines are tail biting, convolutional encoding and decoding. The decoding is done here with a very simple wrap-around Viterbi decoder. This wrap-around decoding is not good for small code rate, for large code rates. So this is these here. It's even going up where the quality of the code goes down, but the decoder gives up here. So forget this. That's not good. A second region here. Here's the decoding time, and I would say at 1 second we forget the rest. So that's the remaining what we have. I just told about Joe's with very large constraint lengths. It would be very interesting where it would be placed here. I think you use about maximum 1 second decoding time or faster. It should be here. Don't know. What I want to show is that tail biting codes are very good for our cases where we have very few information to encode. And this is made for, in this case, 60 bits of information. And you see that the tail biting code with very small constraint lengths even at 12, reach the lower bound to about 0.4 dB. That is a good result, and the decoding time is just more than a tenth of a second. But there are codes which are much better, but unusable. Synchronization and phase recovery, I told at other places about that. Here only some results. Block synchronization means we have to place the received block in time and in frequency space. We must know where is the first symbol, and we must know where's the carrier frequency. That's not easy if the signal is very, very low. Here, you know, from ZS6EME, there are in the diagram all the peaks. I made a very simple own program for all modes. In this case here, a result of ZS6EME at -30 dB. And we have here the time, and there the frequency, and the peaks coming out. This only is good if there is no frequency spreading. The Doppler spreading makes it worse. Here, another again result. And I have 3 diagrams here. One for nearly no Doppler spreading at -33 dB. The peak is well here. If the coherence time is only 1 second, a little bit Doppler spreading, the signal only is detectable as at -30. And if you have large Doppler spreading, the signal only can be detected as -72 dB. We must use some sort of pilot pattern to find the signal. What the space probes do not, they synchronize once and then all is running. ZS6EME uses 63 symbols for pilot, so an energy ratio of 1/2, which costs 3 dB of the total system. PSK2K has 1/3 with 1.8 dB loss, and the new mode QAM11 has another modulation, sends the data bits on the real part and the pilot on the imaginary part, and at half of the amplitude, so we have only 1 dB loss, and this can be varied. Now, some words on the QAM11 mode. Nearly the same source code as in PSK2K. For example, CQ contest DE my core. Source bits are 56. And in any case, in all my modes, I add 15 check bits. If it is received and decoded, the check bits must perfectly fit to the received source bits. If one bit is different, the complete decode is thrown away. The data bits, a simple tail-biting convolutional code gives these data bits and so on. So, a look at such a phase synchronous mode versus ZS6EME. I tested with Joe's program where the limits are. We have here the coherence time. That is my channel simulator for Rayleigh channel, or for the fading channel. And here is the SNR for the BER 50%. JT65A runs in problems at these coherence times. Submode B is somewhat better, and C, as you know. And the question is now, where will a phase coherent mode be? Especially QAM11 was designed to reach, no, not to reach, to approach the sphere packing bound, which is down here at minus 34 dB. And the result is encouraging and very disappointing at the same time. Encouraging because it indeed, on the Gaussian channel, comes down to minus 32 dB. But here we have an EME conference. We must ask, where is the EME channel? Oh, the gigahertz guys will say the channel is here, the coherence times. 70 centimeters might be here, and 2 meters sometimes here, and so sometimes it goes indeed here. Only 6 meters is in any case here. So a phase coherent mode seems to run only on the low bands, are low, 6 meter and 2 meters. So a few minutes, limits of correlation. We ask, what can a receiver do with an actual input signal? And it adds, here's the accumulated knowledge of the operator at the receiving end. What can the actual input signal add to this already known knowledge? In a normal decoder, the code is defined by an algorithm, and the algorithm decodes the message symbol by symbol. In deep search, the algorithm compares the received signal with n given patterns and determines the degree of agreement, and then no more than the best fitting pattern, the pointer to the best fitting pattern is obtained out of the received signal. In JT65, this pointer is used to address the previously known message and to display it on the screen. The displayed message itself is by 100% out of the internet. And the amount of information received by correlation, that's a general formula, not only valid for JT65. If you have a correlation with n patterns, this is the maximum number of bits you can receive. Indeed, the amount of information received from the other station, if you subtract the identification of that station, there's not much left, because only these patterns, these 3 patterns, are checked. So what the other station can send to you is this, logarithmus dualis of 3, 1.585 bits. That's the maximum you can get from the other station. And here are the results for deep search. The theoretical limit is here a very simple, exact mathematical formula. Is this curve, that is PSK. The red line is for FSK, 2FSK, also a theoretical result, but no such simple formula. Then I made simulations, real simulations, and they exactly fit this theoretical line. Then I took QAM11, and this is this curve. The difference here has several reasons. Then I made a simulation with 4096 patterns. This is the result. But I must say, a very important point, these 4 curves are computed with the synchronization being perfect. So we must know exactly where the signal is. Then this is valid. Then I said to my own, that's not the real case. We must find the signal. Therefore, I made a 2 FSK real transmitter and a simple real receiver and simulated it, including the search for the signal, and these results are here. The same, because the program is independent from the mode for JT65, is here. Note the general, the sphere packing bound for our modes is here at minus 34, and the theoretical deep search is much below. The practical is about here. This is only one example of the 2 FSK pattern with search for the signal. And you find at minus 36 such an FSK signal of 168 bits. Very nice. A second one. That's a correlation of JT65 signal at minus 33. Very nice peak. Oh, that's a complete program for the JT65. And okay, we stop here. The time's out, but this is of course not the end. Any questions? So we are out of time, yes?
We have a little time. No? No question.
So, thanks, Klaus, for your very interesting presentation.
Oh, okay.
Give me the PowerPoint later, so I can.
It's not PowerPoint.
Okay, so it was all live. Okay.
Yeah.
Fantastic. Fantastic.
Ah.
Okay, qua you have the pointer. Okay. Laser beam and
Let's go and see, okay? Okay, good morning everybody. My name is Alex Artieda, Soluciora 6 Echo Mike Echo. Most of you know me as HB9 A.R.I. I will present today an optimized EME reception based in Linrad and WSJT running under multiple polarization. The agenda today will be the small introduction, what is happening now. I will not talk about Faraday rotation. I think so we have a nice lecture this morning. I will just mention, and this topic is recurrent the last EME conferences and will be continue in the future. I will speak about traditional errors when we compare software and sometimes hardware also. I will present this multi-polarization configuration based in Linrad and WSJT, sorry. I will speak a little bit about some usual wrong statements because we finished in the last line, the previous line, the questions, is WSJT better than MAP65? And that is, for the last 4 or 5 years, a recurrent discussion in chats and in Moonnet, and many people have their own opinion and experience. And I have my personal experience also in HB9Q, quite is dated more or less during the last 4 years. Okay, I need to talk a little bit this part, Faraday rotation. As you see this morning, is still a problem in the lower bands, and it will be a problem forever in the lower bands. That means in the last years, I think so many contributions happens to fight against Faraday rotation. And I'm talking about mainly about adaptive polarization systems. This starts with probably the first adaptive polarization system I know coming from Live Offspring. And then MAP65 arrived using the concept of adaptive polarization to defeat Faraday rotation. I will say adaptive polarization today is a mature configuration. Personal, from my side, with more or less 200 IQ Plus radios sold and running in 144 megahertz, I will say a lot of people adopt like de facto the adaptive polarization to improve their RX performance. Nevertheless, improper configurations from an adaptive polarization system could produce also mixed results. And not only in the adaptive polarization, but I see then if the system is not properly deployed and configured, you could have maybe something like input rubbish, output rubbish, and that is obviously. Yeah. Now, that comes to my mind that if we want to compare software, if we want to say, or if we want to put ourselves in the adventure to point with our finger, this software is better than the other one. First of all, you need to have a properly platform to do that. And this is one of the main problems when people compare, in this case, WSJT and MAP65. Who recognized this one? No. I call the infamous BNCT because one of the most common errors for all those who want to have several decoders and system runnings is they just take the RX line, tap the RX line, install the infamous BNCT. In one side they put one computer with MAP65 or with the ARIQ Plus, and in the other one another radio with another AD and AD converter and with another software. That means, guys, definitive, please do not use the BNCT to tap your EF if you want to do serious comparison, because MAP65 depend of the phase information to do a properly job. WSJT don't care about the phase. And if you use this one, you destroy your adaptive polarization system. Anyway, we need to avoid errors when we compare hardware, that means, or software also. If we're talking about an adaptive polarization system, and if we want to put ourselves in the delicate position to say this software is better than the other one. We must preserve amplitude and phase in both channels in the adaptive polarization system. And this is a precondition you must have. Means I wrote an extensive guide for the IQ Plus explaining how your coax lines, antennas, preamps need to be set up to really have an optimal result. As I said, avoid the use of VNCTs and calibrate both channels to preserve the nature of the signals, even if the cables are the same. Most of the times are not the same. And well, if you have access to a vector network analyzer, you can measure all your cables and everything. But MAP65 have embedded a very powerful option called the find the delta phi, quite most of the users unfortunately never use. Based on that, in all these discussions, more or less 4 years ago, together with Danny, we decided to embrace ourselves in this tedious configuration. This is nothing new. That means I need to give the credit that the first real multi-polarization configuration based with Linrad and several software running in parallel was implemented by Roger Ress, Whiskey 3 Sierra Zulu. Roger? Where is Roger? Hello, is Roger? And he did the first initial serious comparison between both softwares, and he documented extensively in internet. Well, I took I inspired myself in the job of Roger, and we implement that with some differences. I will not stop in the configuration. Everything is explained and detailed on the proceedings. From the computer, what do you need, how Linrad need to be configured, what some tricks you need to do with the BFOs in Linrads, etc. But let's go just review a little bit how this one works. You have your, this is laser? It's here? No. Well, okay. We have in the upper part the adaptive polarization system. Obviously I put the IQ Plus. I can put the WSE converters also, but I like the IQ Plus also there. And the idea is you have a centralized computer who is doing mainly the job. If you don't have the resources to run one single computer, you can offload the job in different computers. But the advantage to centralize everything in one single computer is time synchronization and the way how you can organize the displays. Well, we have two layers. If we talk about the OSI layer model, we have the hardware layer in the upper part, the software layer in the lower part. As soon as the signals coming from the IQ Plus enter your audio card and are inside the computer, we have a main central instance called Linrad Master, who is taking care of doing the ED conversion, apply noise blanker, etc. And the Linrad Master will be responsible to split the stream of the data in two main streets, let's say. One will go directly to MAP65 via the traditional local network, local host, or you can use another computer with another cable. And the other, and that is go via the traditional port 50004. Then another output from the same Linrad masters will go to 4 Linrad slaves. The idea is to produce, to take the information coming from the Linrad master and send that information to 4 different WSJT software. Could be WSJTX, could be not only MAP65 and WSJT, could be even, I test the configuration to compare in different polarizations. Time ago, CW skimmer to see if it can decode CW or not. That means the platform can be used for different software. Due to the fact that WSJT knows nothing and he don't care about the phase of the signal, that means he has no adaptive polarization routines, we select every slave in a fixed position, in a fixed polarization. Horizontal, vertical, plus 45, and minus 45. Leif suggests me several times we can use 6 or we can use even 8. I think so. The difference between 6 instances to 4 instances in the worst angle is no more than 0.35 dBs. That means 4 is a practical number. The idea is this platform present to both streets. I'd say the street of the WSJT and the street of MAP is presenting the same signal coming from the same antenna, from the same preamps, from the same computer in the same period of time without altering the phase information, especially in the case of MAP 65. That means this platform is in service for a little bit more than 4 years in HMIQ. We start doing several experiments. And in the beginning, I was really convinced that WSJT decode much better than MAP 65. But with the time, I need to review my statements, and we conclude some things later. Now, what motivated me also was some wrong statements, and someone's very funny, means a lot of people published something like that. No? I installed MAP 65 to run in parallel with WSJT, and I confirm many times WSJT decodes when MAP 65 not. Definitive Joe need to do something. And then, well, a lot of people make opinions. Time to time, Joe Taylor show up in the reflectors. He has very interesting statements regarding that. No? Or for example, another one. After doing a properly research for several months, I found WSJT decodes much better than MAP 65. I asking myself, what is a properly research? We never know, because you never know what kind of a selection or what kind of systemic or methodology or metrology was used. I always ran both programs in parallel, and WSJT decode down to -30 when MAP 65 stopped most of the time at -26, and so on and so on. We can fill this room of all these kind of comments. I will say WSJT decode better than MAP 65? I don't think so. In the past, I think yes. But you know, time to time, we need to review our statements. And I don't think so. Because after 1 year of grabbing in logs and more or less 2 terabytes of data, I found that the situation where WSJT decodes and MAP 65 not happens in less than 1%. Honestly, the number is 0.72% in the amount of data I grab. And that happens only in signal-to-noise ratios between -27 and -30. Now, the problem is, what we don't know is how many of these non-decodes in MAP 65 happens due improperly calibration on the adaptive polarization system. And my proposal, and what I'm presenting here, is not a trial between both software, is a very proved platform where you can really test and when you can really collect information. Definitive delta phi calibration on MAP 65 will affect the performance in MAP 65. How much, I don't know. This is something maybe Joe can answer. But if that delta phi is properly calibrated, you will correct mostly your errors in your adaptive polarization system. And in this way, I will say when I talk with people regarding this calibration, and because I create the IQ Plus and I have a lot of friends and customers running the IQ Plus, I ask in always, how do you manage? What do you calibrate IQ image rejection? Do you use noise blanker in Linrad, etc., etc.? And I found a big number of people doesn't know about delta phi calibration, or they know and they ignore, or probably they don't know the impact. No? Now, my conclusions are simple observations are definitive not enough to demonstrate the performance of any particular software or hardware. And that is important is a must to keep integrity of the data to avoid alterations and produce wrong conclusions. That demand to have a stable and well-configured platform, and this is what Roger inspired me with the first attempt. It was in 2012, I think so? Yes. It was in 2012 when he did the first system, and then in HB9Q we was also playing a little bit with this kind of configurations. To do a properly comparisons, specifics between MAP65 and WSJ, the definitive MAP65 need to have the delta phi calibrated. That means this for me is like the beginning. This is an invitation of try. Now, we have an increment of the performance. I will say sometimes yes, because if we jump in the statistical lower indication, less than 1%, when WSJT decode, and this decode is the DXCC you need to have your WAC or a rare grid or a very rare expedition, then it has some value. It's not easy to set up. The proceedings is full of information about how to do that. And it will be very nice to see other ones doing properly comparisons in properly platforms and share with everybody here. The last not least is, I'm not a guy oriented in the statistical, is the information obtained need to be refined and properly analyzed. I think so after the statistical job Flavio and Giorgio did, I think so they will be good candidates to grab in tons of Excel tables and logs to do a better statistical analysis. That escape of my interest, but for sure we will talk with them. Okay, that is, and if you have any questions are open, and I reach my time. Okay, that's it.
Many thanks for
Thank you.
So it's a pleasure to be here, and I had originally sent my files under PDF to save, 12 megabytes. Anyhow, I'm Al, K2UYH, and I'm going to talk about offset feed dishes for 1296, particularly stress offset feed dishes. See if I can figure out how to run this thing here. That wasn't the way to do it. How do I move this? This doesn't move them forward? This? No, I maybe got to point this way? No. No. Here. I'm just... this. Oh, not on. You got one that works? This works. Okay. Oh, no, let me see. Is it short? I think we're, this works as a pointer, which I like. That's great, but I need a move. How about you just press the space bar when I tell you? Okay? Excuse me. This is the story of my life. If it can go wrong, it will go wrong. And if it's an EME contest, it's that way squared. So I'm pretty good at dancing too, and I have bird calls and stuff like that. But I was going to say, while we try and get the second slide up here, is that this presentation is not so much for the group here, because most of you are experienced. My objective here is to get more people on EME, which is we all want to do. And I must admit I'm biased toward the higher bands, though I've been certainly on 2 meters and 220. Here we go again. Let's see. Here we go. So I said, so my objective here is to get more people on EME, and particularly on the higher bands. And one way, the big difference between Tropo and EME is the antenna. A lot of the folks out there who seriously approach Tropo operations can operate EME if they just had an antenna or they pointed their antennas up on the moon. So what I'm really going to ask everyone here is to think about these ideas and pass them on to your local radio clubs, the local people you're dealing with, to encourage them to get on EME. And in terms of the outline here, I'm going to talk about how I got started. I'm going to talk about why a stress dish is a good call to get people to get started on EME. I'm going to talk a little bit about construction and mounting and performance. And here we go. Okay, so because of the interest, I got interested in EME back in high school. That was a long time ago. I won't even tell you how long ago it was. At the time, anyone who was interested in EME and that was back in Sam Harris's days, W1FZJ, you just talked about dishes. So the dish is the way to go. I was a 2-meter operator back then. And so I figured for operating 2 meters, what I needed was a 60-foot dish. You worked it out. This is about where you had to start off with. And this was the first dish I ended up working, which was, getting put together. That was a 30-foot dish. But if you look at the ends of this had extensions to extend this thing on to 60 feet, because I figured that's what I needed to make contacts on 2 meters with a dish. But I soon realized that was going to happen very rapidly, so I moved to 70 centimeters, where a 30-foot dish would be very, very effective. And, anyhow, that was a stress dish, the concept of using a stress dish. And stress dishes are easy to construct. They're light in weight. And one of the big things for me back then, as someone who was just finishing up high school, was they were low in cost. Big issue for me. I had very limited resources. You didn't get that much working after school. Fixing radios is which I was doing at the time, mobile radio repair. Later, I got into the broadcast industry before I finished up school. But anyhow, so cost was a big issue. And I don't know if this is totally true, because gain is gain. Gain is a function of aperture. The bigger the aperture, as you have, the more gain. But one thing that doesn't say enough is that you don't have to be the best constructor. You start building up Yagis, you better make sure those Yagis are properly tuned. Yagis, if you want to get the real gain out of them, they're not real forgiving. The same thing when you phase them up and match them up. You got to be careful. Dishes are very forgiving. You can do a pretty, I'll use the word, pretty poor job, and you can still get gain out of a dish. So that's one of the nice things about a dish. I made my first EME QSO in 1971 using this stress dish. There were about 4 or 5 stress dishes between them, but I was pursuing my education back then, so I was moving from different places, different things, and I never seemed to get my act together until after I really got my first job, and very quickly I got this dish up, which was a 20-foot stress dish in 1971, and worked a number of you here on that dish. This dish that you see was used at W3CCX after I used it, and moved on to the dish I have presently in use, which is a 28-foot non-stress dish. I keep doing this. So what is the stress dish concept? Well, the stress dish concept is that if you take a tube, a rod, even any sort of long element, a spoke, and you bend it, if you do a small amount of bending, you'll see that you get it's an approximate parabola. You get parabolic curve. So it seemed like this was an easy way, without a lot of measurements, frankly, a lot of work, to get a parabolic reflector. And indeed, certainly at the lower frequencies, the curve you get by doing this is more than adequate to get a high-performing antenna. And there is some error. That's what I show you over here. And the error depends on a number of things. It depends on the F/D ratio. Larger the F/D ratio, I'll show you, the more error you get. It depends on the length. It's proportional length, but you can still make really big dishes and get good performance on it. People have used stress dishes up to 6 centimeters. I really thought that probably, I started off at 432. That was a good compromise. I could push it to 1296. But Al Ward, W5LUA, I think most of you know, had used a 24-foot stress dish for a number of years. So you can push it certainly up to 13 centimeters. Dick, K2RIW, had wrote a number of articles on using a stress dish on 2300, 13 centimeters. He's mainly using that to receive the astronauts, but so this technique definitely works well up in frequency. And this just, again, is a quick indication of how, based on RMS error and loss, are related on the dish. This shows you, oops. The next slide shows you a relationship. As I said, when you look at F/D ratio, the deeper the dish is, the more error you get. The real points from these slides here is that gain loss, and if you look at about a dB of gain loss from ideal, and I like to make it less than that, but I think it's a reasonable number. You can make a 40-foot dish on 432 pretty easily, and be able to stay within that 1 dB loss based on errors. And at 1296, I figure about a 12-foot dish. Though there are a lot of things you can do. This is really not doing correction to the basic error you get by just stressing it. And I'll talk about that in a moment. When you go to make a parabolic dish, and I don't have real time to get into construction, this just shows you that the way you do this is, this was for a 7-foot dish, and we're cut off here, unfortunately, on the top, but that says y equals 4px, I'm sorry, y equals 4px squared. This is the basic mathematical equation for a parabola. And if you plot that out, you can figure out exactly the curve of your dish and where you are in terms of the height of the dish, or the depth, if you want to think of it, of the dish, versus the radius of the dish. And then each one of these spokes, I think is a good way to talk about them. When you put them together, they give you a parabolic type. In this case, I'm starting off with a parabolic dish of a parabola revolution, a round dish. I showed a stress dish here made up by N2UO, Mark. He does a very, very nice job. He's much better as an artist producing his results here. Very precise, and this is a 10-foot dish he used for a number of years in New Jersey as a stress dish. He'd roll that behind his house, by the way. He'd just take the feed down and roll it behind his house, and then bring it out when he wanted to operate. And then when he moved to North Carolina, where he presently is, he built up a 20-foot version of this. Now, this does probably a little better because what I recommend is that you can correct the dish by putting circles in the center of the dish to correct for the errors of the dish. So if you put just one circle, you'll get significant correction at that point where there's maximum error in building up the dish. Yeah. That's interesting. What happened? Okay. But this shows you if you put an absolute minimum error in building up the dish, how easy it is. This is the dish we use in the Virgin Islands. This dish here is just a few pieces of wood. That's what they are, local wood that was available on the island. We built, there's no correction ring in here, just one ring around the edges of the dish. These don't hold the shape, they're just made to keep the dish from swaying when you're there. This is approximately a 7-foot dish. I gotta have here is one of Zednik's OK1 DFC's feed. Thank you, Zednik. Zednik has made twice supported feeds for the expeditions. One I made about 10 years before this was it P44, P4 in Aruba. We put Aruba on 1296 there. Had a bigger dish, but the feed is there. Notice how, this is what people, they get hung up on details. Notice how simple this is. This is just a piece of plywood right in front of the pole. One of the problems we had was Bill, who was putting this thing together, used a wooden pole, which was, when you start getting the weights on it, that actually broke. This whole dish broke. We put it up the first time, and we had to resurrect the dish completely and put a metal center pole a little bit more rigid on this thing, the way this was put together, and it worked very well. We made, I think, 5 CW contacts on this little 7-foot dish this was from the Virgin Islands. I don't know why this is doing this. What? Because it's me who's operating it. That's why it's doing it. Anyhow, we look at small dishes of revolution, and we look at them. The small dishes are good. What we're seeing off the top here is it says what's missing off the top of the slide here is this talks about the concept of offsets dishes, which I wanted to talk about today, and making a stress dish as an offset a dish over here. And one of the issues that you have, particularly as you go to higher frequencies, can be the size of the feed you have driving the dish, because that feed becomes a blockage. The smaller the dish, the more blockages. This is not as bad as you think it is, but it can be, when you're looking at a dB and you put something in there and you start looking at the area, it can be significant. It's much nicer if you can bring your feed mechanism, your feed stuff, outside of the center of the feed. So going to an offset dish, that solves that particular problem. It also, as I'm going to show you, offers advantages, not obvious, and big advantages in terms of assembly and mounting of the dish. Most people think that the parabola of revolution should be the easiest way, but not necessarily. And offset dishes are made up so that you use a part of the surface of a parabola. That's maybe obvious, but all you do is you take a portion of the parabola, because it doesn't matter. All you have to do is get your energy on the surface. And so the idea is you illuminate a portion of a dish. I should have brought a picture in here because it makes it so clear. VE4MA has been using for several years an offset dish. His offset dish is part of a 10-foot TVRO. He just takes about a quarter of the TVRO, mounts that, and illuminates the quarter of the TVRO as an offset dish. Voila, you have an offset dish made out of a regular dish. And if in his case, he just didn't want the effort of trying to get a full 10-foot dish mounted and working, and he makes good contact. So you can think of it as a quarter of the surface. And there are variations that I'll show you. The feed point, the key thing is the feed point does not change. You have to move the feed horn. Well, what this does is it moves the feed horn out of the main beam of the dish, so you get rid of the blockage problem. You have to move, of course, the feed horn. I got to point this out. You don't want to point it this way. You want it to point at where where you want to illuminate, where the surface of the dish exists, but the feed point itself is still the same place, okay? When you do this, the feed horn that would be illuminating this full dish is now only illuminating a portion of the dish. So you need a deeper dish to make the feed angle small enough, that one that you can easily get to illuminate that dish, because you want your energy. The key things here is not to waste power. You don't want to send your energy outside of the dish. You don't want to have what's called spill. You want to illuminate the dish. And there's a trade, of course, between how much spill you have and the noise, because you don't want to receive also noise outside the band, outside the surface of the dish. Anything that comes into the feed becomes generally noise that you don't want. So this design issue of how you illuminate the dish, and I'm not going to talk about this here, but you need the feed to match the surface of the dish. And so generally, if you're going to make an offset dish, it's preferable to use a deeper dish. But now you gain the disadvantage the disadvantage becomes an advantage in an offset dish, because now your feed has to match this surface. And so even though the dish has a low F/D ratio, the effective illumination is like as if you had a much shallower dish. And this gives you the approximate ratios over here. So if you had a typical 0.45 or 0.46, that gives you a F/D of 0.9, equivalent of 0.9. So if you wanted to, something which works out very well about the 0.5, 0.55, you want the actual dish you're making this to be based on a 0.35 or 0.34, something about this. So this idea of what the F/D is, you want to use a deeper F/D for an offset dish than you normally want to use for a shallow dish. Again, this is just a matter of design of the feed. There's quite a bit of flexibility. If you're going to take one of Zednik's feeds, for instance, and feed this, then you want a deeper dish so that the feed that you would use for a normal dish would work for the offset section that you're operating on. Here's an example of a 7.5 offset dish here. The advantage, I said there's an advantage to going to an offset dish. One of the big advantages is that you can use less spokes. So this uses just 5 spokes. You just lay, it's a flatter surface, so you just lay the screening across it. This uses 5 lengths, in this case, the example of how you can make something up of wood. Basically, you just go down to the local, you have Home Depots here in Europe, right, or something equivalent of that. So you go and you get some material. This doesn't have to be, of course, wood. It can be aluminum, it can be fiberglass, anything that has a reasonable stiffness to it. This dish used around a 0.530 F/D, and this gave a nice size for about a 90-degree angle feed horn, typical of what you might use to feed a normal dish here. You can, oops, I wouldn't mean to do that. I go too far. Huh. Boy, see? And I'm still learning to drive, too. Okay, this is what I wanted to show. This just shows, this is the center of the dish. It's just a piece of plywood. That could be aluminum plate. There's a lot of ways. I know we have very creative people here that you can come up on how you might construct this or make this up, so you can get one of your friends to get on 1296 who's on Tropo. And this is a weekend project. It's not the type of thing that you spend 2 years figuring out how you're going to get on EME. Let me try this. The secret here is very light touch. That's the secret to this. This just shows you the ends of this. Very simple. You just overlap the pieces. You put this together and you throw the screening on. And this just shows you some more shots of this here. In this case here, what we're doing is we're pulling the spokes to the feed point with ropes to hold this in place, and then throw the screening on the surface. And this shows you the end of the dish. One of the things that's important, when I first made these up on the offset dish, there's a lot of stress where you mount your feed pole to the dish, and if anything, that needs to be reinforced. You want to reinforce that area. There's a lot of stress there, and when I first started making this, one of the mistakes was that I didn't provide enough enforcing. You need that pole, because there's that you're going to mount from also, to be strongly attached to the center section that the various spokes come out of. I showed this here is because you need some way of adjusting, because you want the angle of your feed to illuminate the dish surface. Okay, I'm here. I'm just showing if you're going portable. It's pretty easy to put this together to portable. There's not much to it. There's some screening. Oops, I did it again. Some screening. Your centerpiece. This is the mount over here that I was using for this, and I probably could have used a much simpler mount. I'm sure you can think of a lot of ways to do this. One of the nice things, and I'm trying to illustrate right over here, is an offset dish can be mounted very, very close to the ground. You think of getting your dish up, and there are, if you have blockages, there can be problems, but most of the time we're worried about how do we stow this thing so the neighbors don't see it. How do we stow it so it doesn't get destroyed in a storm, right? It was very nice if you could lay your dish right on the ground, right, when it's not in use, and this allows you to do that, because if you look at it, this is the thing that's holding your feed antenna right here. So you attach, and this is where you want a strong connection. You want to brace this. There's more stress than it first looks at this point, because the forces are from here to here. So but this is your pivot point. So if you lay the dish down, it's pointing straight up like this here. And on a stress dish, you can actually disconnect the ropes that are holding or guy lines that are holding those pieces, and you let this thing just lay flat when it's not in use. And to work on the feed, of course, you just tilt this over and you bring the feed down to the horizon. It's very easy to do this. I was using a mount I had available to work on antennas with, but I illustrate how this thing looks when you can lay it down and down toward the ground. One of the things that is a problem with the offset dish versus the parabola of revolution is that the individual spokes tend to be long. If you want to go out on a trip and you want to take this on a plane, you want to keep the individual pieces very short. And if you do a parabola of revolution, you basically have half the length, if you think about it, because you're producing the dish with smaller sections. One of the things you can do, and I've been through the mathematics, you can take the center hub, and you got to be creative here. This was an example of making up a 20-foot offset dish, but you can take the same concept. You make the center hub larger, and you could make it break in part into pieces or reinforce it. So there's very little difference between the center and the amount of offset here. So you just build these points up a little bit here, and you bend from that point there, and you still get a very acceptable curve, parabolic shape, but now you can make your individual spokes that the dish is composed of shorter. You can also get a little bit more area by having a couple short pieces on the end. There are a lot of variations you can do to increase the size of the dish. This is just the concept of the 20-foot dish. In this arrangement here, the largest segment, this is the cross braces, here are 5.5 feet. This is for the 20-foot example. The longest piece, as I was saying, can be a problem, but this is partially solved by extending the center hub. So you can reduce the length of the pieces here. You start bending at an offset of about 1 inch, so you can just build this up and offset at 1 inch, and the spoke lengths now are reduced by about a third. In this case here, rather than carrying 20-foot sections with you, you can carry 9-foot sections in this example, which are a lot easier to transport and take someplace. And you can do a lot of different variations. But you can picture this. This is, again, one of Zednik's feeds illuminating this 20-foot dish. So if you don't want it, you want to make a big signal, you can go on and use an offset dish out at more like 20 feet. And this illustrates the beauty of mounting. You can just have this thing, down on the ground like this, and then you bend it over to where you want it. When I got through this is the list of parts. I'm a big proponent of doing things easily, and I've used this both with parabolas of revolutions and portable and different options. And this is a plumber's delight feed. Plumber's delight mount. So you just need one of those T-sections that Alex was telling you not to use, but you can, with a T-section, you can make very nice mounts. You just slide on the threads of the pipes. You don't have to do a lot of machining to make this up, and it really works. So, in conclusion, what I've shown you here is an inexpensive and simple way of making antennas for portable and for home on 23 centimeters. And though the focus here was to get more people on 23 centimeters, because I know a lot of tropo out there that could just build a small dish like I was showing you there of the 7-foot variety on a weekend and try it out on the moon. but this will work on higher bands and lower bands as well. The dish I showed you there, the 23 centimeter offset dish, provided about 8 dB of sun noise, and 3 dB over. I tested it against a long loop Yagi, which is a common Yagi used on 1296. So I tested against, I was getting 3 dB more sun noise than I get out of the single loop Yagi. It's relatively easy to assemble, very quick to assemble and mount. And you can mount it, as I point out, very close to the ground and store with the dish flat on the ground, still connected to the mount. So that's the ideas here. The one other thing I would say, because I think I still have a few minutes here, is that one of the things this shows you is that you can take dishes that you wouldn't think could work at a particular frequency and make them work at much higher frequencies. So that's another message I'd like to get out. I've been using a 28-foot dish that I have had up for about 44 years. So I probably have the record for keeping something up. Obviously, it's too small, and I got to think of ways I can do to extend it. But I've been extending a different way, and that is using it up on the microwave bands. I've operated that and had a number of years and made good QSOs with it on 3 centimeters. It should not work at 3 centimeters. The opening on the dish is of the hex material is more like 3/4 of an inch. So it has a lot of spill up on these frequencies. It was never intended to operate up at these frequencies. It's a pretty decent dish at 6 centimeters. Amazing what it does. So a lot of you have antennas, and they maybe not work optimally, but if you want to, try your tropo systems you have out up on the microwave bands, don't be afraid to take your dish and a dish that should not work and try it out at these higher bands. I think you'll be pleasantly surprised, and then maybe you'll start doing the same thing I'm doing, in that working on a better dish solution for the higher bands. Thank you.
Any question? Coming.
Okay, so everything was so clear, we don't have questions.
Al, I'm interested in your comment about using dishes on higher frequencies. Have you any idea how much worse your 28-foot dish was with that spacing than it should have been if it had the correct spacing?
I'm sorry, you're saying, there's one question I'm hearing, that is using the dish at higher frequencies.
Yeah.
Okay. The best example would be DL3YMK, Mike and Monica operations. They used, I think it was something close to 18 feet, 20 feet, excuse me, I got to think in meters maybe. No, but they used before. They went out, when they first started out on the higher frequencies, they used their stress dish, basically. It's basically a stress design they use portable all over the world, and they use that up to 6 centimeters. They never use it on 3 centimeters, but they were able to use I think it's about 18 feet, about 4-meter dish, and they use that up definitely successfully up to 6 centimeters. They've more recently gone to a smaller dish for their microwave applications. Now, you were asking a question in regard to wood.
Sort of really mesh size. I mean, everybody has the sort of standard view of 1/10 of a wavelength, but I mean, does it drop off like a stone?
No,
is it 20 dB worse, or is it 3 dB worse?
No. In theory, you can get by. In theory, without usual, I have another curve. I didn't put it up there on mesh when I talk about dish design, but the limit's around a 1/4 wavelength.
Right.
You don't want to run a 1/4 wavelength because there's a huge amount of spill. I remember at 1296 around, and I'm using U.S. standards of around 2 inches, but at 2 inches, you had a spill of around 60 dB. In other words, the feed through the mesh was about 6 dB.
Right.
On that. Now, that may sound terrible, but it really isn't. When you work out the loss you get, it isn't bad. Interestingly, I notice at 6 centimeters that when I'm using my big dish, that and it first bothered me. I said, you know, everything is, you know, it doesn't bend or anything, but when I go up toward the dish pointing overhead, okay, my performance seems to drop. I don't hear as good echoes, signals are not as good. And I was saying, what's going on? Well, you know what's happening is, it's very interesting, I'm getting my spill, because I have spill definitely at 6 centimeters with the dish by itself. The spill is looking, you look at where it's going, and most of it's up to space. I'm at 30 degrees or so angle. Most of my feed through is looking at space, low noise. As the dish goes straight up, then everything is looking back toward to the ground, and so I'm picking up in ground noise by the angle that the dish is pointed. So if I have poor feed through, poor spill, when the dish is low, it's not as much of a problem as when the dish is high. You know, I look at that, you'll be surprised. I was surprised at how much difference it makes in performance. Aren't you just?
Please wait.
Al, did you ever measure the RMS error of a real stress dish
Yes,
compared
yes.
to the theoretical dish?
Yes. I think there's one of the curves there shows you measured versus.
And the second question I have, because of the shape, not the shape of the dish, the form of the dish is in vertical and horizontal is much different. So did you see any problems regarding the feed horn, that you have different illuminations at the edges? So it could be very different. Well, normally we try to have minus 10 dB at the edges. So what do you think are the illumination at the edges?
I have to clarify your question. It's not a stress dish, because a stress dish or a regular dish, you know, how you're trying to produce a surface. Yeah. And it doesn't matter if you use a stress dish or a regular dish, your requirements in terms of illumination are basically they're the same. Okay? If we look at an offset dish versus a parabola revolution, you're saying this is a matter of how you design the feed. This is where an offset dish gives you an advantage, because if you have a shallower F over D, okay, and that was the case, then you can design your antenna to have a better beam pattern. And this gets in the design of your feeds. Feeds are not all equal. You can design your feed. This is why if people use the I'm looking for a word here, but the rim around, you take a scalar ring. This is why people use a scalar ring, or they use better in many cases. Scalar ring turns out to work out very well for a deep dish, but not for a shallower surface. They use a multi-mode type horn to get a squarer pattern out of the feed horn. One of the things to think about this, I think we're all familiar with filters. If you use a one-pole filter, the filter is very, it drops off very broadly. It's not real sharp. If you go and take two filter tune sections and you couple them together, now you start getting that square. And that's what you're doing with a dual mode horn. I don't know if this has been explained, but what you're doing is, it's just the same way as you're squaring up the skirts of a filter, and now that will give you a better illumination pattern, because ideally what you want is a uniform pattern across where the dish reflector exists, and then nothing when you go beyond that. And it's always a compromise, but you can do better by using a multi-element horn or multi-mode horn to get this more complicated squarer pattern.
That's not what I meant.
Okay.
What I meant is the pattern on the dish, this is all understood. Because if you look to your surface from a very simple stress dish, it is like a triangle. So you have to eliminate a triangle. And at the lower side, so more to the ground, if you put the dish to the moon, then you have a lot of, you can see a lot of the grass around, yeah? And
Yeah,
maybe
yes.
you get up more noise from the ground. Did you have any experiment to observe that problem, or you never
No,
try?
but you can do some projections. It's now a question of whether you just make a quarter of the dish or you make 60% of the dish. It's the way you're talking here about when you design your offset dish, how wide do you make the offset dish, and how do you, because you can picture it. If you picture a beam, a round beam, and what you're saying is at the corner of the offset dish, actually, when you start working out area and you look at this, it's not too bad because there's not a lot of area you lose. But
Okay,
here.
thank you.
Morning, so we go outside and have a few refreshments and some snacks, okay? The sessions will resume at 2 o'clock p.m., 2:30, sorry. And I remind you that behind that wall, that if you go down the corridor and on the left, you will find the measurement lab, and in front of that, there's another space for the little market and tabletop presentations.